Hello, everyone. Thanks for having me. My name is Shani Toledano. I'm a co-founder and CEO of HTBioImaging. My background is technology. I have a science degree in mechanical engineering, specialized in heat transfer and thermodynamics, and almost a master in AI, artificial intelligence. Before establishing HTBioImaging, too long. I spent 10 years in the aviation field as a UAV pilot trainer in the Air Force and R&D and system engineer at IAI, the Israeli Aerospace Industries. At my last position, we developed simulators for flight. And together with my team, I founded HTBioImaging 3 years ago. My R&D team is here, so you can ask them questions later. They developed it. I'm just presenting. So, we have invented the new image modality for early cancer detection. Today, 45% of cancer patients will not survive, and most of them is due to late detection. The main reason is that the doctors do not have all necessary tools and data to see the cancer, and this is why we are here. So we have invented a new image modality for early detection of cancer. Our system is non-invasive, safe, and produces an immediate results. Let's take a look.
Experts agree that early detection of cancer is a major contributor to the successful treatment of all cancer types and cases. Yet detection and diagnostics are the weakest links in oncology healthcare. Current cancer diagnostic methods may involve harmful radiation. These facilities are large, expensive, and scarce, making them inaccessible in the doctor's clinic. But above all, they rely on human perception to decipher, slow to produce diagnosis that may be arbitrary and inevitably inaccurate. HTBioImaging has developed the first 4D thermal diffusion imaging system, a revolutionary new cancer imaging technology that enables safe, real-time detection of cancer in its smallest manifestation and earliest stages. The HT handheld device is an all-in-one solution combining a heating unit and thermal imaging sensor that captures the thermal patterns expressed by the heat transit through the tissue. The unique characteristics of cancerous tissue to dissipate heat in an abnormal specific way is utilized to enable thermal pattern detection of much greater resolution. HT's technology produces thermal scans that are far more accurate and detailed, locating points of interest as highlighted images, which are evaluated by the proprietary HT algorithm, enabling faster, accurate early detection at the palm of your hand. HTBioImaging presents a new groundbreaking method to locate, evaluate, and diagnose a wide range of cancer types. This new branch of diagnostic imaging can be integrated with standard imaging solutions to produce a functional imaging representation of suspected tissues to better evaluate cancer type and risk. Coupled with big data analysis, the HT system will amass new valuable data sets from multiple cases, producing a new diagnostic resource for institutes and facilities, continuously enriching the oncology study and practice. Small, fast, safe, and accessible, the HT device will pave the way for future applications and technologies that will transform the oncology landscape. HTBioImaging, new data, new chance for life.
So, the system is an active thermal imaging scan. It's based on thermal diffusion. Thermal diffusion is a process of heat flow inside materials. We heat the tissue. Cancer and normal tissue transfer the heat differently, and we are able to see this signal and translate it into an image. The image shows clearly cancer versus normal tissue. The method could be used to detect lung cancer, oral cancer, prostate cancer, cervical cancer, and more. We decided to start with oral cancer. After a preclinical trial in mice, we've completed a clinical trial on a pre-biopsy patient in the oral cavity. Before the biopsy, we did our test, take the pathology, and train the system. We have currently 2 active sites in Israel. One is Shiba Tel HaShomer and one is Asaf HaRofeh. We did 45 patients so far. And now we will dive into the algorithm and the learning system. So the input is a temperature map from an IR camera that records the temperature of the heated and cooled tissue. This is a video of how the input looks like. So you see that the video is quite uniform. You cannot see any features or any properties of the tissue from the temperature image. So we moved to 2 different approaches. One is the machine learning and the other is the deep learning. In the machine learning, we did some classical algorithm. We started with the feature extraction based on heat models and mathematical models that we've developed. Then we did data analysis, feature selection, and at the end, classified cancer and healthy tissue. For the deep learning, we put the raw data signal, the temperature versus time. Then we used the unsupervised system in order to extract the features. And at the end, the classifier was a convolutional neural network system, supervised system. For the 2 approaches, the output would be a heat diffusion map, which is correlated to a cancer probability map at the end. The main approach for us now is the machine learning flow, but I will show also the deep learning results that we have. So the reason is, of course, the amount of data. Here we are showing 21 patients. We did so far 45. So for the machine learning, again, the input is the thermal video versus time. We do feature extraction, then data analysis. We select the best features and classify with the Gaussian SVM. At the end, we'll have the map diffusion, heat diffusion map. So in order to do a good training, as we don't have the pathology ground truth for each pixel, we had to select sites. So we selected small sites, which no questions about their cancer healthy label. And this helps us to train the system better. So for healthy patients, we took 2 separate healthy sites. For abnormal patients or cancer patients, we took 1 cancer site and 1 healthy site. So the temperature versus time signal of each pixel in the site is now analyzed separately. Overall, we had 62 features, which calculated per 1 pixel. For each pixel, 62 features. Then those features, of course, represent the properties of the tissue in terms of heat transfer and physical model. And then we took the 62 features and select the best features by a feature selection process. At the end of this process, we put the data into the classifier, the SVM. So each pixel is giving now a probability of being cancers. 0.5 is the threshold for now. So above 0.5, that would be cancer in our system. Of course, the threshold on the probability can be adjusted in order to demand maximum sensitivity in the future. This is one very excited case, just because this patient had a cancer on the tongue, but we couldn't see the cancer. We couldn't see any suspicious area or margins of the cancer or any evidence. But we did our test and put on top of it the heat diffusivity map, which is the probability map of the machine learning approach. You can see here not only the cancer, but also the intensity of the cancer, while red would be cancer and blue would be healthy. You can see, of course, the location of the cancer and the margins of the cancer. This is another case. Here you could see in the optical image the lesion, but the problem is that cancer and normal lesion will look the same. So before biopsy, you can never know if this is cancer or not. This is the problem that we're solving at first step. You can see the steady state temperature image, which is, again, quite uniform. You cannot guess where is the tumor or to understand the margins and the location, and you cannot see any features here. But with our diffusion map, you really could see, again, the cancer in red and its margins and location. So this is the confusion matrix. We had 80 sites totally out of 21 patients. We did a transformation from the site method to the patient. And we've got sensitivity of almost 91%, specificity of 100%, and overall accuracy of 95%. For the deep learning approach, so we took, again, the input as a thermal video. We used an unsupervised in order to extract features from the raw data signal. Then we moved to the supervised learning in order to classify cancer and normal tissue. And at the end, we had a cancer probability map. The unsupervised network starts from the raw data. Autoencoder network train the system in order to learn the signal features. At the end, the output of that box would be features map or feature maps. So for each feature, we'll have one map. And this is how we moved to the next stage, which is the supervised network. The supervised network got as input a lot of maps. Each feature has one map. And the output was the classification, cancer versus normal. The thing here is very interesting is that we took the problem from the signal analysis issues and problem into a computer vision problem. And those are the heat diffusion maps or probability maps. You can see the healthy and cancer ground truth, in which the results are quite good. Of course, a lot of data is required in order to do good and better deep learning system. So what's next for us? First of all, to scale up the data. We just signed contract with the University of Florida in the United States to do a 300-patient trial in order to, first of all, cover all potential oral lesions. For example, precancer lesions, inflammation, etc. And in order to do better deep learning. We are working on data diffusion between the thermal diffusion map and the optical image, which can extract more features from. We are working on the pixel tracking. One of the problems is that the patient moves and the operator moves as well. So we need to track each pixel. And we're moving now to from a local database to a cloud database with IBM. We have high quality partners. One of them is the Reshut HaChadshanut, Israel Innovation Authority, University of Florida, Shiba Tel HaShomer, Technion, IBM. This is it. Thank you for listening. If you have any question, please come.